In this session, I'd like to introduce Laplace transform of some functions. First one is a Laplace transform of a periodic functions. So function f is a periodic function with a period of t. So this means f t plus capital T is equal to the ft. This is the definition of the periodic functions. So Laplace transform the f is expressed using the definition of the Laplace transform. Then we split into the two parts. One of the integral 0 to the period of the capital T. And the other one is a second term is a capital T to the infinities. We change the variable from the T to the P. So T is defined the T plus P's. Then substitute T equals T plus P. So first term doesn't change, but second term is changing using the change of the variable from the lower case of the T to the lower case of the P. So T is changing from the lower case of the T equal capital T plus P. And this is also capital T plus P. And the dt is equal to the dp because the capital T is a constant values. And the lower limit is changing from the capital T to the 0. And the integral with respect to p. We use the definition of the periodic function. So this ft plus p is equal to the fp. This part is exponential minus s capital T times the exponential minus sp split into the two parts. And the exponential minus st is independent of the p, so we can move out of the integrals. And the rest of the part is exactly equal to the Laplace transforms. So we have a same expression of the Laplace transform in the right hand side and the left hand side. Then we move the second term to the left. Then finally we could have an expression for the Laplace transform of the function of the f. In this expression we could find the Laplace transform of the function of f with a definite integrals. Lower limit is a 0 and the upper limit is a capital T. Is a period of the function. Next, I'd like to introduce the unit impulse. The unit impulse function is a delta sub a, and t minus t sub 0 is defined. When the t is changing from the 0 to the t sub 0 minus a, it becomes exactly equal to the 0. So this part, this is 0. So t between the t sub 0 minus a to the t sub 0 plus a, it's the magnitude of this function is 1 over 2a. This is 1 over 2a. If the t is larger than the t sub 0 plus a, it becomes 0. So this is the function. Actually, if you calculate the areas of these regions, height is 1 over 2a. And the width is equal to 2a. And the height times width is 2a times 1 over 2a. It becomes 1. So areas under this function is 1s. Because of the 1s, we call this unit impulse. And using the unit impulse, we'd like to introduce the Dirac delta functions. Dirac delta function is defined with a unit impulse. This is this equation. So a is approaching to the 0. Then unit impulse of the delta sub a is approaching to the Dirac delta function. Dirac delta function is a very strange characteristic. At t equal t sub 0, it goes to the infinities because the height of this function is 1 over 2a. If the a is approaching to the 0, this function is approaching to the infinities. So height is go to the infinities. So this corresponds to this part. Even if the height is go to the infinities, So width approaching to the 0. So height is approaching to the infinities and the width approaching to the 0. Area is keep having the constant value of the ones. So if you integrate Dirac delta functions, areas under the curves is keep having the same value of ones. This is the Dirac delta function. So we'd like to find out the Laplace transform of this Dirac delta function. So unit impulse function is expressed with a unit step functions. So this is a unit step functions. So we use two unit step functions. One of the unit step function is a t minus t sub 0 minus a. And the other one is a t minus t sub 0 plus a. This function is produce the unit impulse. Then we'd like to find the Laplace transform of the unit impulse functions. The Laplace transform of the unit impulse functions is expressed the Laplace transform of the unit step function and the unit step function. This is the Laplace transform of the unit step function. This is Laplace transform of the unit step functions of the t minus t sub 0 minus a. And this is Laplace transform of the unit step function t minus t sub 0 plus a. Okay, then it becomes the exponential minus s t sub 0 minus a over s for the first terms. The second term is exponential minus s t sub 0 plus a over s. Then we could find the common of the exponential minus st sub 0 and the exponential sa minus exponential minus a over 2sa. So this is the Laplace transform of the unit impulse functions. Then we'd like to find out the Laplace transform of the Dirac delta functions. Then a approaching to the 0. Then this part is approaching to the 1s when the a is approaching to the 0. Laplace transform of the Dirac delta function is expressed exponential minus st sub 0. So especially Laplace transform of the Dirac delta function of the t, you can substitute the t sub 0 is 0, it becomes 1. Laplace transform of the Dirac delta function becomes equal to the 1s. Next, I'd like to introduce the error function. When you study the statistics, you might have studied the error functions. Error functions and also the complementary error function are defined as this error function. It's a 2 over square root pi and the integral from the 0 to the x exponential minus u square du. This is error function. Complementary error function is a 2 over square root pi and the integrals from the x to the infinities exponential minus u squares. Of course, we know that 2 over square root pi integrals 0 to the infinities exponential minus u squared du equal 1. We have already know. If you don't know that these integrals, you should review the Gauss integrals. By using these integrals, actually the sum of the error function and the complementary error function becomes 1. So in the practice, I ask you to find out the Laplace transform of the complementary error functions. Okay, this is the end of this session, and also this is the end of this chapter's Laplace transforms. Hopefully you enjoy learning the Laplace transform.